There is a mystery at the heart of our universe. A paradox so enormous it seems to defy the very fundamental laws of physics. It's not a star, nor is it a galaxy. It is something much, much darker. It is a black hole. For decades, we have understood black holes as quiet giants, growing slowly by consuming the matter around them. There's a strict theoretical limit, a boundary known as the Eddington Limit, where an outward pressure from its own energy would prevent a black hole from eating any faster. Exceeding this limit would be like trying to force a river into an already full drain pipe. Theory said it was impossible. But recently, we found black holes that do exactly that. Cosmic eaters so voracious, they make our theories obsolete. They are cosmic predators that defy all expectations. How could these monsters be eating faster than we ever thought possible? How did they do it? And what does their existence say about the true nature of the universe and how its laws might actually work? Stick around until the end of the video to uncover the full story. And don't forget to like this video and subscribe to the channel for more amazing discoveries. About 1.5 billion years after the Big Bang, a distant galaxy blazed with such brilliance that even from a distance of over 12 billion light-years, it remains one of the brightest objects in our night sky. So bright, in fact, that the algorithms designed to classify cosmic objects overlooked it. You see, an object that far away should be incredibly faint. Its light has had to travel halfway across the universe to reach us. A nearby star, on the other hand, would have that kind of luminosity. And that's exactly what our computers thought it was at first, just another single star in our own Milky Way galaxy. But it wasn't a star, it was a quasar. And at its heart, a black hole, an enormous black hole. And it was hungry. Named J0529-4351, this black hole is not just one of the brightest quasars ever discovered. It's consuming matter at an unprecedented rate, equivalent to one sun every single day. Think about that. Every day, a star just like our sun vanishes forever. The accretion disk surrounding it, a vortex of gas and dust heated to millions of degrees, spans an incredible 7 light-years in diameter. 7 light-years. That's a distance far greater than the gap between our sun and the nearest star. This is the largest accretion disk ever known, a monstrous, swirling ring of destruction. The light from J0529-4351 shines over 500 trillion times brighter than our sun. And all of this light and heat originates from the collapse of matter into a black hole with a mass of approximately 17 billion suns. These numbers are difficult to grasp. 1 star a day, a disk 7 times the distance from us to Proxima Centauri. A monster that reached its gargantuan size just 1.5 billion years after the entire universe began. J0529-4351 is an unignorable challenge to our models. Our theories struggle to explain how a black hole could get so big, so fast, in a universe so young. What we thought was a slow, steady evolutionary process now seems more like a high-speed arms race, and something must have been powering that race. It's possible there's an observational bias in our sky surveys. The algorithms we use to find new objects are trained to recognize patterns. And J0529-4351, with its extreme brightness and immense distance, broke those patterns. It was dismissed as an anomaly, something that must be wrong. This raises an unsettling question. How many other extreme objects have we missed? How many theory-breaking objects have our algorithms filtered out? J0529-4351 suggests that the early universe might have been teeming with such monsters, hiding in plain sight, just waiting to be found.
Before we continue, I'd love to hear from you. What do you think about this discovery? Do you believe it changes the way we understand the universe? Or is it just another puzzle waiting to be solved? Share your thoughts in the comments. I'll be reading them.
The story doesn't end there, though. It's not just about the rate of growth. It's about a core concept of astrophysics, the Eddington Limit. Imagine you're blowing on a feather in the palm of your hand. The outward force of your breath counters the inward force of gravity holding the feather down. The Eddington Limit is essentially the same idea on a cosmic scale. As a black hole pulls in matter, its accretion disk gives off a tremendous amount of radiation. This radiation creates an outward pressure, and at the Eddington Limit, that pressure becomes so strong it balances the gravitational force pulling matter in. The Eddington Limit was a barrier. At least, that's what we've always thought. But then, another black hole was found, one that defied this idea to an absurd degree. Discovered with the James Webb Telescope and the Chandra X-ray Observatory, this black hole is named LID-568, and it is consuming matter at a staggering rate, more than 40 times its own theoretical Eddington Limit. 40 times! LID-568 isn't a massive monster like J0529-4351. It's only about 7.2 million suns in mass. What makes it special is its extreme eating speed relative to its relatively small size. It's experiencing a feeding frenzy so immense that according to our theories, it should not be able to exist. And it's not a fleeting event. It's sustaining the super Eddington state. So how is it not ripping itself apart? Observations show that LID-568 is spewing out a powerful outflow of gas and matter. Astronomers believe this is the answer. This outflow might be acting as a pressure release valve by carrying away the excess energy and matter, thereby allowing the black hole to continue consuming without becoming unstable. This idea is a huge shift in our thinking. We used to see outflows as merely a consequence of accretion, but LID-568 suggests they may be an enabling factor for extreme accretion, a cosmic self-regulating mechanism to allow black holes to grow faster. And that means that black holes could be undergoing rapid episodic bursts of growth rather than just a steady increase in mass. This explains a major mystery: the presence of massive supermassive black holes in the early universe. They don't have to start big. They can start small and then undergo a brief but intense period of hypergrowth. It also shows that the Eddington Limit isn't an impenetrable boundary, but a soft limit, a point at which other physical mechanisms kick into gear. It's like trying to pump up a tire. When the pressure inside gets too great, you don't just stop. A small hole would appear, releasing the excess pressure and allowing you to continue pumping. These black holes are those leaky tires, and the gas outflows are what keep them from blowing up.
The discovery of J0529-4351 and LID-568 has profound implications for our models. When we combine these two discoveries, a new picture of cosmic evolution begins to emerge. We have J0529-4351, our gargantuan monster, the fastest growing one ever known, already in existence in the early universe. And we have LID-568, a smaller black hole that shows that super Eddington bursts are possible. These discoveries challenge our seed scenarios. Current theories of supermassive black hole formation often rely on two scenarios: light seeds formed from the collapse of the universe's first stars, or heavy seeds formed from the direct collapse of massive gas clouds. However, if super Eddington accretion is possible, then the initial mass of the seed may be less important. A tiny black hole could grow into a monster in a single intense accretion phase. This also has implications for the co-evolution of black holes in their galaxies. If a black hole can gain mass so quickly in a short, violent burst of accretion, the feedback it produces could halt the growth of its host galaxy. Think of a black hole as a child going through a growth spurt. It eats uncontrollably for a short period of time, and then it stops. Its growth is not a continuous process, but a series of extreme spurts. This could explain why some massive galaxies in our universe have monstrous black holes at their centers, while others do not. The relationship between the two could be far more complex than we imagined. And these aren't the only challenges black holes are posing to us. Recently, scientists detected a black hole merger that created a final black hole with a mass of 225 suns, a number considered a forbidden mass gap for standard stellar revolution models. That means there's another formation mechanism at work, possibly a hierarchical merger of smaller black holes, or growth in dense environments like active galactic nuclei. The challenges posed by black holes, whether through accretion or mergers, suggest that our understanding of extreme physics is still incomplete. These are the most important data points. They don't fit our models, and that means our models are either wrong or incomplete. And that is a beautiful thing. The most extreme, the most anomalous objects in the universe are the ones that reveal the limits of our knowledge.
They are like mirrors, reflecting back the gaps in our theories. J0529-4351 and LID-568 are not just cosmic record holders. They are signs that there is something fundamental we're missing. Perhaps the Eddington Limit is only one part of the picture, and more complex physics are at play, allowing black holes to behave in extraordinary ways. Maybe the evolution of the universe is not a slow, steady process, but a series of dramatic, episodic events. These discoveries remind us that even the physical laws we have taken for granted can have their exceptions. And every time we find such an exception, a new door opens, a door to a deeper, richer understanding of what made our universe and what makes us. So is the Eddington Limit truly an impenetrable limit? Perhaps not. Perhaps it's just one of many boundaries that are waiting to be crossed. And these cosmic monsters are there to show us the way.